Just let me know if you can see the slides now, or
It
no.
was.
Yeah?
Yeah, yeah.
Okay, cool. Yeah, okay. Thanks for the invitation. So yeah, let me give a quick self-intro. So my name is Yu. I'm currently a senior researcher at Microsoft Research, AI for Science. I'm based in Berlin, and uh, today I'm gonna present this very recent preprint from our team called Enhance Diffusion Sampling, which is to combine the enhanced sampling approach with the diffusion models to enhance the sampling efficiency for free energy difference calculations. Um, right? Oh. Yeah, so the molecular sampling problem has been known to be quite challenging. Specifically, we want to compute the observables from the equilibrium ensembles, P of X, and we've been using empty simulations or Monte Carlo methods to do this estimation, but there are fundamental bottlenecks such as, first of all, the slow mixing. For example, the MD trajectories are time correlated, and the long-lived metastable states could trap the simulation for quite a long time. And also, even with independent samples, the rare state could be quite difficult to sample as well. The low probability states could be exponentially suppressed from the free energy difference. And one example from this slow mixing is think about the protein fold versus unfold. It could require crossing the large free energy barriers, and a single trajectory may never observe the transition. And we've seen in previous works from, for example, D-shell research, people have tried to specifically selected 12 proteins which are relatively small and are very fast folders. But even that, with the very specifically designed Anton supercomputers, the unbiased MD simulation still requires, in a millisecond level to converge the state transitions for a single protein. And another example is this bond and unbound from molecular dynamics simulation. So this is a showcase of this Barnes-Bastar, which is a very well-studied protein dimer complex. If you start from the unbound state to bound state, to simulate towards the bound state, then it will take about 50 microseconds in terms of the time scale, corresponding to 1 year of GPU time, which is already quite expensive. But if you want to go the opposite way, then that's another like 6 orders of magnitude more expensive, which is essentially infeasible. Um, Traditionally, people have used the enhanced sampling methods, and the core idea is basically you can sample from biased distribution with different approaches, applying different sorts of a bias, and then you find a way to reweight them back to get the unbiased statistics. Some examples include umbrella sampling, where you can apply multiple umbrella or harmonical windows. And then you can, for each window, generate samples under such a bias, and you can combine all the samples um, with methods like MBAR and also metadynamics. You can apply Gaussian, repulsive Gaussian hills to as the biased potential, and then replica exchange or parallel tempering. You can have simulations from different temperatures so that the low temperature simulation can benefit from sample diversity from the high temperature. And then there are also other methods such as free energy perturbation, thermodynamic integration that try to compute quantitatively free energy difference or delta delta G. And we've seen quite a lot of success applications in with those methods in combination with MD simulations. But also, on the other hand, it's also quite known that those methods are still challenging to use in a sense that it requires a lot of manual or ad hoc setups or tweaking, and also methods such as umbrella sampling or metadynamics requires good selection of bias coordinates like collective variables, and it's usually unknown a priori. And there is also the chicken and egg problem. If you want to get a good estimation of the collective variable, you probably already needs to have a good understanding of the slow modes. But then to sample the slow modes, you will probably need a good collective variables to do that. And if you don't select a very comprehensive CVs, then you might miss some slow modes like orthogonal states from hidden barriers. So one toy example of this to show is you can see at the figure at the bottom. On the left-hand side, you could have a landscape of two metastable states well connected, and then uh, the enhancer sampling using the x-axis as the reaction coordinate can get a pretty good coverage of it. But then on the right hand side, this different energy landscape can have orthogonal states at the top, and then running the enhancer sampling along the x-axis reaction coordinates can easily miss the orthogonal states due to the hidden barrier here. And here we're considering the IID sampling approach for the slow mixing problem. Sorry. And this whole motivation is based on our previous work called BioEmu, which is protein ensemble generator model. So it is basically a diffusion model built on top of the AlphaFold architecture plus so using the diffusion model to map the Gaussian process noise, the Gaussian distribution noises to the Boltzmann distribution protein structures. And so this work is, let's say we have a given protein sequence, and then we can pass it to the AlphaFold evoformer to get the sequence representations. And then we can start with different Gaussian noise structures and pass it to the structure module to get the score estimation. And then starting from different Gaussian noise, we can get different protein structures for a fixed sequence. And then this diffusion model can give us IID sampling of the protein conformational ensembles. So this work has been published on Science last year. So we will use this model as a base method. Just to give a very quick overview of how this model was obtained. So we had three training stages. The first one is pre-training on some synthetic data from the AlphaFold database structures so that we can kind of enable the model to get qualitatively diverse conformations. And the second stage is we fine-tune the model on MD simulation data, including a lot of publicly available data sets and in-house data sets so that we can enable the model to emulate the MD simulations to try to reproduce the Boltzmann conformational distribution from the force field. And the third stage is a top-down training approach where we try to incorporate the experimental observables, including 500,000 protein folding free energy measurements, so that we can further correct the bias from the MD simulation, like the insufficient convergence or the bias from the force field, so that we can achieve, like, kind of get closer to the real equilibrium distribution by this experimental data correction. So here it's an example of how the model distribution looks like. Here we have this comparison of the bioemu prediction distribution versus the MD distribution. So you can check the bottom left plot, we have compared those two conformational distributions on the two-dimensional projection of the teacup plot. So you can see that this IID sampling is quite efficient and can actually get the metastable states and transitions. And another capability of this model is the protein folding free energy prediction. To give you a brief idea of how this is done, so basically we start from Gaussian noise and keep denoising to get the clean sample, and then we can apply reaction coordinate, which is a predefined analytical expression, just trying to looking into the contact of different protein residues, and then use this to quantify like how folded a protein looks like. And then using this reaction coordinate, we can get the statistics of how many structures from the ensemble are folded and how many of them are unfolded. And we can compute the fold and unfold ratio from the ensemble to estimate the folding free energy delta G. And then we can use this to compare with the experimental data as both the benchmark as well as designing the laws for training. So uh, one example from the bioemu paper is this comparison with experimental benchmark. We have shown the test set performance below like MAE below like 0.9 kcal per mole, and the coefficient Spearman's correlation coefficient about 60%. So it has shown quite impressive generalizations. But then there is one problem. So in the previous data set, we actually have all the data within all the delta G data within the range of 5 kcal per mole. But the protein can go, much more stable than that. So in this case, to give you a concept of the rare state, how rare it is. So even with independent sampling, this ratio can grow like exponentially. So the sampling efficiency kind of struggle a lot. So let's say if the delta G is 5 kcal per mole, then that means we have one unfolded states out of 4,000 samples. And if it's 10 kcal per mole, then that means one unfolded states out of 19 million samples. So this will make the our model kind of basically infeasible to get unbiased sampling for proteins with like 10 kcal per mole. So this kind of motivates us to try to look for approach that can improve our sampling for higher folding free energy differences. And then this can be naturally extended to other problems like binding, which usually can have up to 20 kcal per mole binding free energies. So as I mentioned before, the MD simulations with the enhanced sampling can suffer from the slow mixing problem. But diffusion samplers generally don't need to worry about, things like a hidden barrier because it can perform the IID sampling for the metastable states. But on the other hand, the diffusion sampler can still suffer from the rare states. So we hope by combining those two worlds, we can help to draw the independent samples while at the same time improve the sampling efficiency when there's the rest state. And we have explored the combination with the umbrella sampling, metadynamics, and also this delta G diff, where we basically apply a sort of linear tilting potential as the bias. So the whole like high level framework is basically two steps. The first step is to generate biased ensembles from defined bias potential. So let's say for a given bias potential B of X, we want to steer the diffusion model just at the inference time so that we can sample from these P of x multiplied by the tilting potential. And the P of x, it's basically the unbiased distribution from the original the pre-trained diffusion model. And then here we choose to use this Feynman-Cut corrector for steering at the inference time control. And then in the end, we get the weighted samples, xi, and each sample is associated with a weight. So asymptotically, those samples can achieve the target tilted distribution. And then with that, we can recover the unbiased expectation. So if we only apply a single bias potential, we can just do direct reweighting just by, multiply the bias factor back. And if we have multiple ensembles, then we can use this M-bar methods, which have been combined with the umbrella sampling in traditional MD for the optimal statistics for the observable estimation. So the bias potential is user chosen and defined. So yeah, just to give a quick overview of the steering methods. So here, eventually, we want to sample from the biased distribution for the clean data, and from those methods, we can basically define this time-dependent biased marginals, so that we can have this bias potential dependent of time, where at the beginning you could apply no bias with all the noise, and in the end, we can have the full bias. So that's the kind of final tilting potential that we want at the data level. And in the past year, I've seen quite a lot of publications trying to kind of address this problem, like quantitatively, to get like a quantitative tilted distribution at inference time control. And so people have shown a pure score-based score guidance. It's simple, but generally it's biased. And then there have been approaches like the SMC based methods, so that you can combine the denoising with the reweighting, such that the weight can give you the asymptotic convergence for the distribution. And then there are also can consider like predictor corrector methods, so that the at each denoising step you can perform the corrector steps for multiple times, so that you can actually equilibrate the samples at a certain noise level. And here, what we choose is this Feynman corrector methods, which basically is derived from the Fokker-Planck equation. So basically, it inserts the tilted target distribution into the Fokker-Planck equation, and you can derive the new sets of equations so that it gives you the biased sampling methods. So first of all, we can perform this biased denoising for the sample X. It's basically the unbiased part, the first two terms, plus the bias term given from the bias potential. This is the fourth. And then besides that, there is another set of equation. So this is the time evolution for the log of weight. And this evolution is given by the bias potential and the score. So essentially, in the end, after this time evolution, we will get both the denoising sample and the weight associated with each sample, and then we can reweight all the samples to get the bias distribution of the conformations. And we also monitor the effective sampling size to perform resampling with a threshold of 0.5 or 0.6 or 7, like depending on different applications, so that we will reset the weights to 1 every time upon resampling. So this is the essentially the steering approach that we use. Then naturally, we can combine this with things like umbrella sampling. Here, what we consider is so the first example is the umbrella sampling, where you can consider a collective variable KC, C of X. So it's basically a low-dimensional function for on top of the high dimensional coordinate space, and but then this is also predefined. So, for example, in our case, we could use RMSD for protein or some other coordinates based on the structure, and then for this coordinate, we can uh, like in its range, we can define a sequential of windows, and each window can be seen as can be used for like a harmonic potential centered around the CK here. And then for each window, we can generate steer samples from via the FKC steering, and then collect the weighted samples. Then we combine the samples from all the windows and apply this M-bar approach to iteratively get the partition function and reweight those samples all together to get the unbiased to get the unbiased estimation. So getting back to this toy example that I showed before, so this is the so we set it up with the GMM so that we have the analytical score, and we get a better control to study the effect from the enhanced sampling algorithm. So as you can see, so on the left-hand side, in a case where there are like two well-connected metastable states, the umbrella sampling actually is quite efficient if it's still using the traditional MD. So you can see the blue and orange curve actually both get a decent estimation in comparison to the ground truth. But on the right-hand side, when there is the hidden barrier, then the umbrella sampling with the MD simulation can get quite off in terms of the free energy estimation because it is difficult to cross the hidden barrier and get the other metastable states. While on the other hand, the blue curve showing the diffusion model has no trouble capturing the metastable states. Um, so on the other hand, very naturally, we can also combine this with the metadynamics. Basically, what we can do here is so we can have the same, let's say we can start from the unbiased sampling for a batch, and then we get a batch of samples, and then we can use this batch of samples to define the new bias potential for the next batch. And then for next batch, we can apply this new bias potential, perform the steering, and get a new biased batch of samples. And then we can use the M-bar to get this whole new ensemble, and then use that to define a third round of new set of a bias potential to keep performing the bias batch by batch until convergence. So if you look at the classical metadynamics, the problem is you apply the repulsive Gaussian hues for the bias potential along the simulation. And in the end, the process is quite like a non-equilibrium during the filling up. But in this case, if we kind of run this diffusion model steering with the bias that each batch runs, then each time you actually get the equilibrium distribution at the current bias. And then also at each round, it's quite straightforward to directly apply the M bar because we know the bias distribution at each round. And then here we showcase this algorithm for this one-dimensional double well potential here. So in the first column, this is the unbiased sampling with the ground. So the ground truth is set to be 13.8. So this delta G value is set up based on the weights of between those two different Gaussian peaks. And in the probability space, in the how to say the probability density space, it's quite invisible with the 13.8 delta G. And while in the free energy space, the PMF space, you can still see those two wells here. And with zero point 0.1 million samples, the unbiased sampling still has a quite hard time capturing the other metastable states, and the estimation of the DG is quite off. And then starting from the second column and to the fifth column, we can see how the diffusion model combined with the metadynamics kind of iterate batch by batch. So the first step is just completely unbiased sampling. And then we get a first estimation of the free energy landscape. And then we use that as a new bias potential for step one. And we keep doing it until step three, when we basically achieve the same number of samples as the unbiased sampling. So you can see that first of all, the estimation of the delta G converges quickly. So from step zero to step one, so at step one, we already get a quite close delta G estimation compared to the ground truth. And then at step three, when we have the comparable number of samples, we not only get the delta G estimation right, we can also capture the even the transition state in the middle. So this is the example of the metadynamics. And then we're considering combining this with the actual protein model. And here, instead of consider the umbrella sampling and metadynamics, here we're thinking about directly using a linear biasing potential, this linear tilting potential, so that we don't have to think about, for example, overlapping distributions between different umbrella windows in the coordinate space. And here, just one simple example. Let's say in the folded states versus unfolded states, we've been using this reaction coordinate called the fraction of native contact. So it basically has a range from 0 to 1, so it's bounded. And then if you have the reaction coordinate close to 1, then that means it's close to a perfect folded states. And on the other hand, if it's close to 0, then it's close to it's like unfolded states. Then our idea is like if you apply a linear tilt, then basically you have the same bias strength across the entire reaction coordinate range. And then sometimes we find that a single tilt, if you like tune the tilting slope, then it's also quite efficient in biasing the state population. And we have also proposed this adaptive tilting, which is kind of in a similar spirit as the metadynamics, where you can basically start from a pretty small or zero tilting. So it's equivalent to unbiased sampling, and then you can adaptively adjust the tilting slope to balance the number of populations of both states until they get quite balanced, and then you can combine the samples from multiple different tilting to and combine them with the M bar to reweight them back to get the unbiased estimation. And here we have this example still from this 1D double well trying to showcase like trying to learn like how much we can gain in terms of the sampling efficiency. And honestly, the results is a little bit surprising. Here, we're basically using a single linear tilt, and then we have estimated those tilts. Uh, a previous like or already like assuming like it's like almost near optimal tilting, but then with the adaptive tilting, like the number of samples, it will not grow too much. And here what we do is we apply this tilting to different like different systems with different ground truth delta G, ranging from uh, about 2 kT all the way towards 13.8. And then we want to see compare like how many samples will be needed to converge the delta G estimation if we use unbiased sampling versus if we use this tilting sampling and then reweight them back. And then from the bottom row, you can see how the number of samples versus the delta G estimation changes, comparing the blue and orange lines. And then we take the number of samples that converge within 1 kcal per mole and plot the top right figure, just trying to show the scaling of number of samples required with respect to the delta G. And naturally, the unbiased sampling has this straight line showing that the number of samples grows exponentially with the free energy difference. On the other hand, if we use this tilting, then we get a much more flat scaling. So you can see that this converges with only about like 10 to 100 samples, even in the case of nearly like 14 kBT. And we also found that if you combine further this with the second order integrator, then this curve can actually be further suppressed. And then we try to figure out if the same conclusion can be found in the protein model. So here we try to implement this algorithm to the Bioimmun 1.1. This is our published model, and then combined with this FKC reward tilting. And then we have to kind of adapt this algorithm to such that we can combine it with the DPM solver plus. And then because otherwise we will need much more number of steps to converge the sampling. And we have selected 26 proteins from this database called ProthermDB, such that they have a range of 1 to 6 kcal per mole of different delta G. And we have also excluded 8 of them so that because they don't have a very reliable reference. So the rest are like 18 that we show the final comparison. And the collective variable is we use is a quite simple one. It's RMSD. And we try to figure out if this could even work with the with our diffusion model. And oh, sorry. Okay. And then we can see that we actually can get a quite similar scaling. So if you look at the bottom right figure, the green line shows the unbiased sampling, so this is trying to make a more direct comparison to our previous 1D example. So the x-axis is the unbiased, fully converged, the unbiased delta G, and the y-axis is the number of samples required to converge the delta G estimation. So also naturally the unbiased samples, they align very well along the straight line, indicating the exponential growth of number of samples for convergence. While the enhanced sampling, this gives us a more flat scaling, and the crossover happens at about 3.2 kcal per mole. so that we can, which is like a not very large, and we can already gain like nearly one order of a magnitude sampling efficiency boost from these steering methods. On the top left corner, we show this just for a sanity check, trying to show if this enhanced sampling estimation for the protein folding free energy is biased or not, and we can see a nice unbiased parity here. Um, yeah, so here are two figures from our supplementary, just trying to get like more statistics so you can see like how those 18 systems sampling looks like. So this one quantifies this so-called catastrophic failure rate. Basically, if you do like unbiased sampling, then in a lot of times you don't even get a single folded states, and we were trying to quantify like how much this happens. And another example, another figure trying to show this mean absolute error change with the number of particles from the sampling. So then this one actually corresponds to our previous scaling plot, so that you can see that when the systems have the reference delta G beyond 3.2, like the first two rows, you can start to see pretty good advantage from the enhanced sampling method. Okay, so to briefly summarize, we here try to address this problem of the diffusion model rate event sampling. Even at the IID sampling regime, we can suffer from the rare states convergence problem. And what we propose here is to combine the biased sampling with the steered sampling with the enhanced sampling approach from the traditional MD. Um, so in terms of this approach, so I do want to mention that there are a couple of limitations. So first of all, um, this one is actually it's not for reproducing like physical distributions or like distribution from a certain force field. Instead, you start with a pre-trained model which already samples the equilibrium distribution. And then this method tries to enhance the sampling efficiency for the surrogate model itself. And then if this model itself kind of miss mode or it gets biased distribution, then that will also propagate into the real weight estimates after the enhanced sampling. And second, we didn't eliminate the requirement for collective variables. So our approach still requires a choice of a CV at the first time, at the beginning. So for example, in our umbrella sampling or metadynamics or the delta G diff, in all the cases, we have already predefined the CV and then apply the bias potential. So we also predefine the bias potential itself. And then I think this also kind of illustrates some potential future direction that's combining this with some sort of learned CV or like some CV learning methods as well. And also we have to notice that there have been a bunch of different steering algorithms with different efficiencies. And here our choice of the FKC is like we find this is like a nice approach and we try to use it and it works. And but then there are also some other alternatives. But also the important sampling, it could break down if those different states have quite insufficient overlap. So this sampling variance could be very large as well. Yeah, and our model um, uh, doesn't include kinetics, and so it's just for equilibrium properties. But then that's one of the open direction for the base model itself as well. Just one quick note that the steering algorithm itself is also more expensive for each step compared to the unbiased sampling because we have to evaluate we have to kind of like back propagate the reward with respect to the sample, but the calculation of the reward also involves the score function. So this means that we have to backprop the score function at each step. So it makes it about 2 times more expensive compared to the unbiased sampling. But if we look at our previous scaling, like this constant factor, it's not a big concern. So we have already released the model and code for the base model, and we actually have something to be merged involving this enhancer sampling feature, and will be released very soon. So if you're interested, you can have a look after our release and let us know if there's anything could like interesting or could be fun applications. Yeah, so then that's the end of my presentation. This is teamwork. So yeah, so this is so I have also put the archive number here, so you're very welcome to discuss with me. And yeah.
Great. Um, does anyone have any questions? Just feel free to raise and ask questions.
Maybe I can ask. Yeah, maybe I can ask a question.
Mhm.
Yeah. So I noticed the mention you can do M bar at any time. What does this actually mean? Like any time?
Oh, so here, sorry, just getting back. Yeah, so here it's like every time, so it's like every after each single step, you get like you can get like a new biased potential, and then you can apply that biased potential to sample the new batch. And then you get like a newer batch, and then that newer batch will have a known bias potential. And you kind of know, okay, so this new batch comes from this like a biased equilibrium distribution. So now you can have like different batches coming from different bias potential. And then yeah, it's basically just get back to the M bar.
Why doing M bar? Or why is it different from standard EHANA sampling? Like I assume it's also possible to do M bar and
Uh,
when it's equilibrium.
So in yeah, so when it's equilibrium, but like for metadynamics, the problem is like it's like not really a equilibrium process when you fill up the potential.
I see, I see.
Yeah, yeah. So like eventually, like usually in metadynamics, people kind of just like use the accumulated potential so that the whole landscape become flat, and then they just directly invert the accumulative bias to estimate the free energy instead of using M bar. But like you can also use M bar in some cases. Yeah.
Yes, question.
Yeah, so shall I repeat the first question? Yeah, or we just see the
Oh, yeah, I can read the first question. Does the bioimine work for protein plus ligand in solvent systems, or is it restricted to protein-only simulations? Yeah, so currently our base model, it's just for protein monomers, and it's trained from simulation data with explicit solvent. But when we make the predictions, the solvent molecules have been kind of integrated out. So it's some sort of, like the solvent effect have been incorporated into the model itself. But then right now we don't have the ligand model explicitly in our released model. So that will be for the next version. So the next question is, I wonder what's the physical meaning of hysteresis in these model. Isn't it related to magnetism? Yeah, I'm not sure I understand the question. So generally, I think that hysteresis is like kinetic issue, right? So it's like if you if you have let's say like if you have two different metastable states, then you could have um, if you want to like make the transition simulation, then it might um, take much longer time, or like you might overshoot to get the transition to happen. One example in material, probably it's more relevant to what you mentioned. So from what I know from material phase transition, it's like if you want to simulate, for example, a melting of a certain material from crystal phase to a liquid phase, then you might need to raise the temperature much, much higher than the actual melting point to actually melt the crystal in the simulation. And on the other hand, if you start from a liquid phase and you have to cool it down to a much lower temperature than the melting point, so that you get the crystal structure. So that's a hysteresis from my understanding. And but I don't think the ID sampling generative model will have the problem in general. Um, because like you're not dealing with the barrier crossing, but I don't know this magnetism stuff. Mhm.
Yeah, thanks anyway.
Yeah.
Yeah, and
Yeah.
very inspiring work.
I think if there's no more questions, maybe we could call it today. And thanks again for you to join us today, and see you guys next time.
Thank you very much.